me start recording it. So 1 mole is that, and if you have that many of carbon, okay. Now, some of the carbons are, you guys know isotopes, right? Isotopes are like when you have carbon's number 6,
Mhm.
you can have carbon 12 or carbon 13. So this one is made up of 6 protons,
Mhm.
6 neutrons,
Mhm.
and 6 electrons, right?
Yeah.
And this one
Mhm.
is made up of 6 protons and 7 neutrons and 6 electrons, right?
Right. Just different
So,
math.
yep. So we've gone through that before.
Yeah.
And there are different bunch of isotopes. But if you have, I'll tell you where this number came from. It's just for your, it's not necessary to know at the stage.
Mhm.
If you have uh, the way the chemical these numbers were generated is through this way. So if someone is let's say 170 centimeter, and actually it's 170 point, let's say 1 centimeter, and
Mhm.
from now on, this girl's is in year 11 in CGGS, and we're going to from now on say her height is from now on exactly 12. All right.
Okay.
It's a weird convention.
Yeah.
And let's say someone else is 100 and let's say 77 centimeter.
Mhm.
Then what's going to be her height? So all you have to do is just divide. Let me just take this calculator here. 177 divided by 170. So you see the this girl's height is the reference
Right.
uh, by which they
It's
measure. So you do
1.04.
that,
Oh yeah.
and you get 1.04, which means 104%.
Mhm.
It's just tiny bit higher than this one, right? You
Mhm.
times that by 12, then you get this person's height in terms of this new convention. That's a
Mm.
12.48677, whatever, you know. And that's kind of what we did for carbon 12. So what we did there is, all right, carbon 12 has exactly, all right, by the way, the mass of carbon 12 in kilogram is, let me just bring up some data. So at first, this might be a bit difficult to understand everything what I'm talking about. So carbon 12 mass in kg, I'm just going to Google that right now. And I get, all right, let me just derive that. Okay. Just give me a minute. So carbon 12 has that much mass in kilogram. Do you understand?
Yeah.
Mm-hmm. Now, what we're going to do is we're going to let this guy equal to, we're going to create a new unit, all right? Just as we have, so we can go into classroom and measure people's height
Mhm.
and pick this really popular girl and make her height the standard. And
Yeah.
we just render that girl's height to be 12.
Mhm.
And you can measure every other girl's height in respect to her height, right?
Yeah.
So that makes sense, right? So we can say that 170.1, that's her height in centimeter, and that's going to be 12 unit. Then this will be 12.486 blah 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 unit, right?
Mhm.
That's what we are doing pretty much for the atomic world. So carbon 12 here has this much weight, this much mass, and we're going to let that equal to 12
Mhm.
atomic mass unit, 12 AMU, or simply 12U. And the reason for that, of course, is you see how this 12 matches with that 12?
Yep.
Mm-hmm.
Mm-hmm.
So, what's carbon 12 made up of? It's made up of 6 protons, right?
Mm-hmm.
And made up of 6 neutrons. And then 6 electrons, right?
Mm-hmm.
But most of the mass is taken by what?
By the electron, sorry, the protons
By the
and
protons and neutrons.
neutrons.
Electrons weigh very little, true, compared
Right.
to protons and neutrons.
Mm-hmm.
So how many nucleons are there, girls? How many nucleons? You guys know what nucleons are?
No, I
No.
don't.
Nucleons are the inhabitants of the nucleus.
Oh, inhabitant.
Yeah. So what's in the nucleus?
The
Protons and
neutrons
neutrons, right?
and protons.
Protons and neutrons. So number of nucleons is simply 12. Okay? Nucleon is either proton or neutron. Make sense?
Mm-hmm.
Yeah.
So there are 12 nucleons, and electron you can just ignore that because it's too light, right?
Mm-hmm.
So why not just let that equal to 12 unit? The mass of that is 12 unit, right?
Mm-hmm.
That's very convenient. You can just do that. And therefore, what's going to be the mass of 1 unit then? Can you guys work it out? If 12 unit is equal to that much kilogram, how much is 1 unit in kilogram? I want you guys to work it out. There's no reason for us to make that height to be 12 because of this girl has no feature that is related to number 12, right?
Right.
But here the carbon has number 12 nucleons. That's the reason why we let it equal to exactly 12. Okay, the mass is 12 instead of because working with kilogram is too difficult because it's got like negative power of 26 there, so it's very difficult for us to comprehend. So that's why we're creating this new unit, 12 units. Simply because there are 12 nucleons. And if you divide that by 12, then 1 atomic mass unit is equal to about that much kilogram. Mm-hmm.
Mm-hmm.
Yeah. And that must be, of course, approximately mass of 1 nucleon, true?
True.
Now, do you guys know roughly the mass of a proton and mass of a neutron? A proton and neutron? They're very similar.
Is it just I'm just going, is it one? I'm not sure what one, but
Okay, so this is the mass of proton in kilograms. You can see that that's very similar, right?
yeah. Yes.
Mass of neutron is about 1.674, slightly higher.
Mm-hmm.
This is mass of a neutron. Okay. So that's very similar to 1U, true? So this is roughly, you can say 1U, and this is roughly 1U, okay?
Yeah.
Mm-hmm.
So from now on, just understand that mass of any nucleon is approximately 1U, and that's approximately 1.66 times 10 to the power of negative 27. The reason why this is like, that's 6 there, this is 6 7, right? The reason for the loss is because of when this is some extra stuff. Some of you doing physics, so you might be interested. When particles fuse together, they lose mass, and the lost mass is called a mass defect, and that gets converted into energy, and that's how the sun, the sun is made up of hydrogen, right?
Mm-hmm.
And the hydrogen fuses together, so protons come together and fuse into helium,
Mm-hmm.
and mass is lost, and that mass is converted into energy, and that's how we get the sunlight.
Right. Yeah.
And it can just burn for like billions of years, while losing very, very tiny bit of mass. Okay.
Okay.
So that's year 12 physics stuff.
Mhm.
So that's why when you have carbon, the carbon mass is 12 AMU. When you divide, when you get the 1U, because of the lost mass, when things fuse together to become carbon, there's a little bit of mass lost. That's why that's actually a bit lower than the individual protons and neutrons. Okay. So, but doesn't matter if you don't understand. That's fine. Okay. Now, let's talk about the derivation of Avogadro's number. Okay, so we know that carbon 12 weighs very tiny mass, this much here, and we're going to let that equal to 12 AMU. And 1U is this much. Now, here's a question, very important question. By the way, this one is equal to 1.99268 times by 10 to the power of negative 29 grams, isn't it?
Yes.
Because you just divide by 1,000 to get in grams.
Yeah. Okay.
Now, I want you guys to answer this question. How many carbon 12 do you need to make up exactly 12 grams? So I want you guys to think about that question. Can anyone answer the question? So divide 12 gram by this one, 1.992648 times by 10 to the power negative 29. Then you get this number.
Yeah.
Hold on. Did I actually do it the other way around? Should this be 23? Yes, it has to be times by 1,000 to get gram, right? So I actually made a mistake there.
Oh, okay.
Because we know that 1 kilogram is the same as 1,000 grams, true?
True.
So you had a times by that to go from kilogram to gram, got it times by 1,000. So it's actually 23 gram, right?
Yeah.
Times by 1,000, then 26 become 23. Negative 26 become 23.
Yeah.
And does that make sense to you?
Yes.
Yeah. So you divide this one by 23 there. So my bad. Then what you get is the Avogadro's number.
Oh.
The Avogadro's number. So that's the derivation of Avogadro. That's where it comes from.
Oh, right.
You simply ask the question, how many carbons you need? How many carbon 12? Not carbon 13, not carbon 14, just carbon 12, okay? How many carbon 12s do you need so that weighs exactly 12 gram? And then you get this one. What that means is this. What is the mass of carbon 12? Well, the answer is 12 AMU. And 12 AMU is only this 1.99 times by 10 to the power of negative 26 kilogram. Very small.
Right.
If you have the Avogadro's number much, okay, Avogadro's number much of the carbon 12, then that will translate to 12 gram exactly, right?
Right.
This is the link between, this is known as the relative. You guys learned this already from the, you guys learned that the periodic table, in the periodic table, all these numbers are what? These are
relative atomic mass.
Relative atomic mass, right?
Yeah.
So these units, so it's, if some teacher says that this is the unit for these numbers are grams per mole, Well, practically you can say that, but technically that's wrong. Okay? These
Oh.
numbers,
Mhm.
just think about it. If someone's height is 170.1 and we just say that it's 12, and
Mhm.
this actually doesn't have a unit. Okay?
Mhm.
It actually doesn't have a unit.
Mhm.
Then 177, that's also like that's that, right?
Right.
And doesn't have any unit. So in
Mhm.
fact, these numbers don't actually have any unit. Okay? It's only when you have Avogadro's number much of this compound
Mhm.
that you get 12. Okay?
Oh.
We'll talk about why this is not exactly 12. Okay? So this is 12.011.
Mhm.
In short, this is because it's made up of a bunch of isotopes like carbon 13, carbon 14, carbon 15, etc. You know?
Yeah.
Yeah. So you guys already learned that, I think, when you
Yeah.
did
We.
weighted average, right?
Mhm. Yeah.
So, but when we are only talking about carbon 12, the mass, the
Mhm.
relative atomic mass is exactly 12 and doesn't have any unit. But you can say that you can attach a unit. You can say that although there is actually no unit, you can say that this being without any unit is another unit, and you can just create this AMU quasi pseudo unit, and that actually weighs this much. And if you collect Avogadro's number much of that atom, then it'll weigh exactly 12 gram. Now, what about then oxygen 16? So it's made up of 8 protons and 8 neutrons.
Mhm.
If carbon is 12 AMU,
Mhm.
if carbon's mass is 12,
Mhm.
carbon 12's mass is 12,
Mhm.
then what will be the oxygen 16's mass in AMU? Or what
16.
would be is it really 16? But it's actually slightly less than 16. Okay.
Right.
The reason for that is, so I'm just gonna go for oxygen 16, and if you go to, you see that? That's the
Mhm.
first thing that shows up on Wikipedia.
Oh.
It's that important. So if you just have a single oxygen 16,
Mhm.
which is made up of 8 protons and 8 neutrons,
Mhm.
the mass of that is 15.9949 blah 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 U. So you can say that if you just get rid of that unit, that's
Mhm.
the relative atomic mass.
Yep.
If you attach this unit there, then it becomes the atomic mass unit.
Mhm.
And then if you have Avogadro's number much of this particular atom, then how much will it weigh? It will weigh exactly 15.9949146195 grams. Does that make sense to you?
Right. Okay. Yeah.
Yeah.
Mhm.
Um, I'll prove it to you. Okay. So take a look at this. We know that this is 1U, right?
Yeah.
So I'm gonna do 1.66054 times by 10 to the power of negative 27. That's in kilograms, right?
Mhm.
Now times that by this much U. Okay. 1U is this much kilogram. So times by 15, almost 16, 15.99491461956. Then this is the mass of a single oxygen 16 in kilograms, right?
Right.
Now I'm going to times that by this Avogadro's number that we derive. Okay. We're going to collect that many of that mass. Okay. So 6.022137723. That's 0.01599491462. So it's correct up to there.
Yeah.
And that's in kilograms. So you got to times that by 1,000.
Mhm.
then you get 15.99491462 grams.
Right.
See?
Yep.
So there's a direct transfer from that U to that gram.
Right.
Okay.
Mhm.
Now, obviously, you have two questions, I guess. First question is, why not 16U?
Yep.
Why not 16U?
Yep.
Second question might be, why in the periodic table you have decimals for carbon? Because it's like 12.011, right?
Right. Yep.
I'll answer the second question first.
Mhm.
And this is something you guys have already done, right?
Yep.
So what that is, it's a weighted average of, so carbon 12 has mass of 12. Carbon
Right.
13 has mass of 13, roughly 13, not exactly 13, okay?
Yep.
The only thing that has exactly just integer 12 like that, without any decimals, is carbon 12 only. Everything else,
Mhm.
so I'm sort of answering question 1 here, just half of it. Only carbon 12 will have an integer value.
Right.
Carbon 13, if you look up carbon 13, so carbon 13, what does it say there? 13.00, you see, it's got a bit of decimals, right? So although it's close to 13, it's not exactly 13. But anyway, the composition of carbon 12 is about 99%, isn't it? Let's have a look at the carbon abundance. So this is 1.109%. 1.109%. This one is, if you subtract 100 minus 1.010, then you get 89.89%. 98.8. I think carbon 14, other isotopes, I think you can just ignore them. So if you simply take the weighted average of them, so you go, all right, 12 times by 0.98891. So that's 98.891%. And there's a 13 times by 0.011109, and then divided by, oh yeah, you can just do that. See how you get 12.0011?
Yeah.
So that's how you get that number on the periodic table. In the periodic
Sorry,
table,
I'm just wondering, why did you divide it by 1?
so you can do, there are two ways of doing it. So if you're doing a 12 times by 98.891 plus, and then 13 times by 1.109, and then divide by 100.
Yeah. Oh, right. Okay.
Which is 12 point that, right? But what I did before was I already took divided by 100 already, because the 98.891 divided by 100 is 0.98891, right?
Yeah.
So I didn't have to divide by anything in that case.
Yeah.
I just had to do 12 times by 0.98891, something like that, was it?
Yeah.
Yeah, I forgot. So you can do that, and then also the 13 times by 0.0109. Then I think I've messed up this number here. 981, something like that. I don't know. What was the percentage?
Yeah, that's okay.
Yeah, we can, yeah. 9, yeah. Anyway, so that's the reason why you have decimals, okay? So there are a bunch of isotopes. So in the periodic table, you're not going to get any integer. They're all decimals, you see?
Yeah.
Yeah, they're all made up. They're all weighted average of of different isotopes according to their abundance. Okay.
Right.
Now, So that's enough of introduction to Avogadro's number. Okay. So your school won't teach this stuff at this rigorous level. So a lot of people think that this is unnecessary, but I really like going very deep into the fundamentals and the reason for every stuff that you just take for granted.
Yeah, sure.
That's just my style of teaching. Now, let me just think about what I should teach next. So we talked about Avogadro's number. That's right. Oh yeah, have we talked about why it's not exactly 16 for oxygen? And the reason is back to physics again. So it's a bit difficult to understand. So when, as I said before, when we learned the fact that, protons mass is this, neutrons mass is this, but when you divide the carbon's mass by 12, you get that. And that is similar to the mass of this and this, but not quite, right? And what was the reason for that again? The reason for that happening is because when protons and neutrons fuse together into a single atom, some of the mass is lost, right?
Yeah.
Yeah. So when you look at carbon, carbon is when 12 nucleons fuse together, right? So it lost a little bit of mass.
Right.
And we are letting that equal to 12, right? But then when you have 16 nucleons, when 16 nucleons fuse together, probably it's going to lose more mass, right?
Right. Yeah.
More mass than carbon. That's why when you divide the carbon's mass, whatever that is in kilograms, whatever that is in that's right, kilograms, and by the 1U, you're not getting quite 16, but you're getting a little bit less than 16. You see, you're getting that one. It's a very difficult concept to understand. Because more mass is lost, so it'll weigh less than what it's supposed to.
Yep.
And that's why when you divide it by, when you measure the mass, it's not quite 16, it's a little bit less than 16. So when you look at other, so you can see that when you look at boron, let's say nitrogen 14, nitrogen 14's mass is, it's actually, sorry, that's carbon 14 there. I think I think we have to just move on. I think that's a good enough explanation. It's unnecessary. Does that make sense to you, though?
Yeah, it does.
Okay. What about here? Yep. Okay. That's great. Now, let's go back to this question. It's a very simple one here. So we know that 1 mole is the same as 6.022 times 10 to the power 23 atoms or molecules, right? So, or particles, let's say. Let's first figure out, don't worry about the question. I want you to figure out the molar mass. So all you have to do is, all right, you have 6 carbons, so it'll weigh 12.011 times by 6. There are 6 of those. And then 1 point, I think the hydrogen's number is, if we go back here, it's a 1.008. Exactly, 1.008 times by 12. And oxygen is 15.999 times by 6. So that's how you work out. So if you actually do that calculation,
Mm-hmm.
what number do you get?
I'm just doing that
1.01
now.
times by 6 plus 1.008 times by 12.
I got 180.156.
Yep. So 180, that's right.
156.
That's right.
Yep.
So what is that? What is that number? Well, you can call it many different things. You can just say that's the, if there's no unit,
Mm-hmm.
then just call it 180 is the relative. In this case, this is made up of a bunch of atoms, so you can't call it relative atomic mass. You can call it a relative molecular mass.
Yeah.
Or if you have 180.156 AMU, and that's exactly the mass of. So if you have AMU, that means this is the mass of one molecule.
Right.
And of course, this AMU thing can become easily converted into kilograms, because we know that one AMU or a 1U is the same as a 1.66 times 10 to the power of negative 27 kilograms, wasn't it?
Right. Yeah.
If you simply times that number by that number, then you get what? Then you can get the mass of a single glucose atom in kilograms, right? So
Right.
what was that? So that was the 1U. So I want you guys to figure out, okay, the mass of one molecule, please, in kilograms. Okay.
Of the glucose?
Of the glucose, yes. So that would just equal to 180.156.
Yep.
Times by 1.66 times by 10 to the power of negative 27, right?
Yep. So I got 2.99.
Yep. That much kilogram. So it's very tiny.
Yep.
And of course, that's the mass of one glucose molecule in kilograms. And of course, we can just times this one by the Avogadro's number. 6.022 times by, we just collect Avogadro's number, many of those. And we get 0.180 times that by 100, then you get 1,000, then you get 180 grams, right? We don't have to do that anymore, because we know that as long as you collect Avogadro's number many, there is direct numerical correspondence between the molar mass. By the way, number 2, this was AMU, and that's translated to this much kilogram. Number 3 is just 180.156 grams, and this is the molar mass. So there are 3 ways of interpreting this number. This is grams per mole. So you see, there's a convenience to. So why do we? So in conclusion, why do we use Avogadro's number? Because when you collect Avogadro's number, there will be direct numerical correspondence between the relative atomic mass to the molar mass.
Yeah.
Yeah. Does that sort of make sense?
Yes.
Yeah. That's why we don't have to do. So if you don't have them, if you don't have this technique, then you have to do like 180.156 AMU. That's just tiny mass, which is that much kilogram. And then you see what I did before? Like you did 2.9905896 times by 10 to the power of -25, and then you times that by Avogadro's number, right?
Yeah.
What is the mass when you collect Avogadro's number many? You see how you get about 180 kilograms?
Yeah.
180 grams, you see?
Mhm.
Yeah. So we don't have to do that step, see?
Mhm.
If you have 1 mole or Avogadro's number many,
Yeah.
just go straight from the relative atomic mass, which you can read from the periodic table, and you're going from there to there straight. And
Right.
all that calculation, which was shown over here in the calculator, that can be skipped.
Right.
So that's what you're doing when you're saying, oh, that's 180.156 grams per mole. Okay?
Right. Mm-hmm.
Yeah. All of that stuff is just assumed. And yeah, so that's why, because it's so complicated, as you can see.
Yeah.
Year 11 students are just taught, all right, that's just grams per mole. Just count all these numbers in the periodic table, and that's just grams per mole.
Yeah.
But it's much deeper than that, as you can see.
No, it's really helpful because they just say it's related to carbon, but it's like how is it related to carbon? But
yeah, so
yeah.
we just solved the mystery today, right?
Yeah. Yeah.
Not related to carbon. So this stuff, I find this stuff like pretty difficult to explain, even though I taught this stuff like for many years.
Mm-hmm.
So that's why you'll probably observe that I'm just repeating the same stuff over and over and over, but I just can't help,
Yeah, no, that's okay.
But I hope that helps.
Mm-hmm.
Now, how do we answer this question? Let's first talk about this situation. Okay, so let's try to solve this problem first. Okay, there are 26 dozens of aliens. Okay, and each alien is made up of 6 arms and 6 legs and 12 eyes. Okay.
Yeah.
So total, so the arms plus legs plus eyes is equal to 24, isn't it?
Yeah.
I would like to know how many arms and legs and eyes are there total together among 26 dozens of aliens. All right?
Yeah.
So once you do...
That would be 624 because you just
So you have
timed...
26 aliens, 26 dozens of aliens, so you times it by 12.
Oh, dozens. Oh, sorry. Yep.
Yeah.
And then
you
times
first get what?
So I got
26 times by 12, then there are 312 aliens, right?
Yeah. And then you just times that by the number of arms, legs, and eyes, which is 24.
Yeah, each alien will have 24 of those, right?
Mm-hmm.
Altogether.
Yeah. And so I got
24, then you get how much?
88.
So that times by 24 equals 7,488, right?
Yeah.
Of eyes and plus, legs. So we don't care how many eyes are there, how many legs are there, how many, arms are there. We just want to know the total, okay?
Yeah.
I'm just going to call them features.
Sure.
So there are 7,488 features, okay?
Yeah. I'm just going to be gone for a quick second. I'll be back soon.
Yeah, sure. Let's get back to this one. So this is one way of doing it. But there's another way of doing it, which is you go this way first, times by 24. Then what are you getting here? So what's 26 times by 24? That's 624, right?
Yeah, 624.
Well, what's 624? What does that stand for?
The
goal is to get to here. We want to get to the number of features, right?
Mm-hmm.
So of course you can times by 12 first and get the number of aliens.
Mm-hmm.
Um, and then times by 24, or you can times by 24 first and then times by 12, right?
Mm-hmm. Yeah.
But if I do 24 first, what am I getting? 624 dozens of features.
Oh, yeah. Right. Okay.
Because if you multiply by 24, 24 is the same as features per alien, right?
Right.
What that means is that the alien and alien will cancel out,
Mm-hmm.
and you just get dozens of features. Okay.
Mm-hmm.
But if you multiply by 12 first, 12 aliens per dozen, right?
Yeah.
In that case, dozen will cancel out, and that's why you get what? 12 aliens, right?
Yeah.
Mm-hmm. Anyway, so you get that.
Mm-hmm.
You get features per alien anyway here. And then when you have 624 dozens of features, you times by 12, then you get rid of dozens, right? So you end up with that many
Right.
features. So there's a reason why when made you guys to go through this step, because what we have is 0.260 mole of this molecule, this big molecule. Okay. Now I can times this by the Avogadro's number. Okay.
Yep.
Because 1 mole is that many molecules, right?
Mm-hmm.
So if you times 1 mole is that many, so 0.26 mole would be a little bit less than that, right?
Yeah.
So 6.022 times by 10 to the power up 23 times by 0.26. Then you get 1.5 blah. That many. What? That many molecules.
Right.
Molecule is the word that refers to this whole thing. Okay. So
Mm-hmm.
you see how I drew that diagram? So that's one molecule, inside
Yep.
of which there are 24 atoms, right?
Mm-hmm.
Now, then you multiply. All right, in one molecule, you have 24 atoms, right? So times by 24 atoms per molecule. Then you get the answer in atoms. You
Mm-hmm.
count the total number of atoms like that. So times by 24. Then you get that number.
Mm-hmm.
That's the answer there. So that's the answer to this question. What is the total number of atoms in this many mole of glucose molecules?
Right.
Mm.
Okay.
So you first get how many molecules there are. Because you have 0.26 mole multiplied by the Avogadro's number to get the number of actual molecules.
Mm-hmm.
And then because you know that there are 24 atoms inside one molecule times by 24. Now, go the other way.
Mm-hmm.
Times by 24. Well, this is atoms per molecule. So we know that inside of one molecule, there are 24 atoms. Anyway,
Yep.
times by those two, that's easy. 0.26 times by 24. Then you get 6.24. Well, what's the unit for that? 6.24 represents what? Can you guys figure it out?
Well, 2.6, like not like molecules.
Mm.
No.
This is the number of molecules, and this is the
Oh,
number
right.
of atoms. So that's a pretty big number, right?
Yeah.
But multiply 24, that's not that many. That's not such a big number
Right.
because the mole is still alive. You see how 1 mole
Mm-hmm.
stands for 6.022 times by 23, right?
Right.
Huge number. If you only multiply 24, you get that number. You still haven't got rid of the mole. So this is a mole of molecules.
Mm-hmm.
This is mole of what?
Of
Mole of atoms.
right. Okay.
You have
Yeah.
that many mole of atoms.
Mm-hmm.
Okay. And then you times that by the Avogadro's number, then you can finally get rid of the mole and get this number. Is that a bit confusing?
No, that makes sense.
Okay.
Yep.
But if it's confusing, it's quite normal. Like for example, if you have, it's a bit like this. It's similar to this one here.
Mm-hmm.
Yeah. Give you another example. If you have 100 adults, okay, 100 adults. How many? Hold on. Yeah. So if you have like 100 people, you can go for, sorry, let's say like 20 dozen people, very similar to what we talked about before, 20 dozen people. You can calculate how many people there are first, right? So that's 240 people, right? Times by 12.
Mm-hmm. Yep.
Get the number of people.
Mm-hmm.
And how many features are there? Just let's just count the eyes and arms and legs. Just 6, right? 6 features,
Yep.
right? So just times by that. But if you times by 6 here, you're still keeping the dozen, right?
Right. Yep.
120
Mm-hmm.
dozen. Instead of people, you've now gone to features, right? It's like going
Right.
from molecule to the atoms, because inside one atom you have a bunch of one molecule you have a bunch of
Mm-hmm.
atoms, right?
Yep.
Yeah. So hope this helped.
Yeah. No, that was really
So
helpful.
I'm going to give you some homework. Yeah, I'm gonna give you some homework based on that worksheet. Maybe there's not much time until tomorrow morning, right?
Yeah.